Example problem number 5. Remind me to ask you guys in class whether you prefer to see just the screen here, the slide, or if you like to also see me messing around with all the controls. Anyway, back to the subject at hand. 2 speakers emit identical sinusoidal waves. The speakers are placed 4 meters apart. A listener moving along a line in front of the 2 speakers finds loud and quiet spots as shown in the following figure. The grid lines are spaced at 1 meter. What is the frequency of the sound from the 2 speakers? Well, as we expect, right in the middle of the 2 speakers, right in the center, we get a loud spot because the 2 distances that the waves have to travel from speaker 1 and speaker 2 are equal. So we expect constructive interference here. Then that means there must be some region of destructive interference or a quiet spot, quiet here and quiet here in between the next 2 loud spots. So if this is the first loud spot, then according to our equation for finding interference, the path length difference over here on the left is equal to, right, we know it has to be equal to some whole number of lambdas. Here, right in the middle, m is equal to 0, right, because the path length difference is 0 wavelengths, right? They are equal distances away from the speakers. So here, if this is the first loud spot, then on either side of the central, m must be equal to 1. So let's find the path length difference. M is equal to 1 and solve for lambda. So I've got this distance here is equal to, 1, 2, 3 meters. So I can say, I'll write over here, d1 is equal to 3 meters. I know that the distance between, let's make that a color I can see, between 1 and 2 is 1, 2, 3, 4 meters, right? So here's 4 meters. If this is a 3, 4, oh, guess what the hypotenuse is going to be? You remember your trig? I hope so, right? So here's my D2. Here's D2, here's D1. D2, this is a 3, 4, 5 triangle. That's 5 meters right there. Okay, so delta D, the path length difference, D2 minus D1 or D1 minus D2, it doesn't matter, I'm taking the magnitude, so 5 minus 3 is 2 meters. So now, according to this expression, I know that 2 meters, I'm going to write out the word meters because I have m's on both sides, oh goodness. Well, m in this case is equal to 1 times the wavelength, which means the wavelength of our sound coming out of these speakers is 2 meters, okay? I want to find the frequency of sound. Well, I have to remember that the speed of sound is something like 343 meters per second. I think our book uses 340. They like to round to 2 sig figs. No big deal. The frequency then of the sound coming out is V over lambda. That's 343 meters per second. Ooh, it's getting a little messy in here. That is a frequency equal to, if you plug this into your calculator, something like 172 1/seconds or hertz. And there you have it. Oh, and if you saw this in class for the other section, this originally, or if you noticed for both sections, this originally said quiet here, but we know that's a mistake because we know that when the distances are equal from 2 speakers to a listening post, you must have constructive interference, so it must be a loud spot.